Imagine a foot race. The excitement, the adrenaline, the sheer determination of each runner to cross the finish line first. The finish line is your computer program's goal. It's the point where everything comes together, where the code achieves its purpose. Runners are different parts of your code, all trying to reach that goal. Each piece of code has its own task, its own journey, but they all aim for the same endpoint. In a race, the order they finish matters, right? The sequence in which they cross the line can determine the winner. Now, imagine some runners cheat, cutting corners or getting a head start. This disrupts the fairness and integrity of the race. That's a race condition in code. It's when the timing of different parts of the code affects the final outcome. Formally, a race condition happens when the outcome of your program depends on the unpredictable timing of these different parts of code. It's like a race where the timing of each runner's start and finish can change the result. It's like the final score of the race depending on which runner cheated the most. The integrity of the result is compromised. This is especially important in computer programs that do multiple things at once. When tasks run concurrently, the order of execution can become unpredictable. Just like our sneaky runners, different parts of the code can interfere with each other if they access and change shared resources at the same time. This interference can lead to unexpected and often undesirable outcomes. Let's talk about threads. Threads are like the individual tasks that a program can perform simultaneously, much like how multiple people can work on different parts of a project at the same time. Imagine threads as our runners in the race. Each runner is trying to reach the finish line, just like each thread is trying to complete its task. In many modern programs, we have multiple threads running concurrently. This means that several tasks are being executed at the same time, which can make programs run faster and more efficiently. They all have access to the same data, like a shared bank account. This shared access can lead to complications if not managed properly. Now imagine two threads trying to deposit money simultaneously. Both threads are trying to update the same bank balance at the same time. Both read the balance, say £100. Each thread thinks the balance is £100 and plans to add its amount to this balance. Thread 1 adds £50, making it £150. It's ready to update the balance. But before it can write the new balance, Thread 2, still working with the old £100, adds its £25. It doesn't know about the £50 added by Thread 1. It writes £125 back to the account. The £50 added by Thread 1 is lost. Uh-oh, money has vanished into thin air. This is a problem because the final balance is not what we expected. This is a classic example of a race condition. A race condition occurs when the outcome depends on the sequence or timing of uncontrollable events. The final balance depends on which thread wins the race to write the data last. This can lead to inconsistent and unpredictable results. This unpredictable behavior can lead to some very difficult to find bugs in your code. Debugging these issues can be a nightmare, as they may not always occur in the same way. Timing is the biggest culprit in race conditions. In the world of computing, timing can be everything. Just like in a race, milliseconds can make a huge difference. It's impossible to predict exactly when each thread will execute its instructions. Each thread operates independently, and their execution times can vary wildly. It's like trying to guess the exact order our runners will cross the finish line, even with all the cheating. The unpredictability adds a layer of complexity that can be maddening. Even tiny differences in timing, perhaps caused by other programs running on your computer or network delays, can completely change the outcome of your program. These minute variations can lead to vastly different results. This makes race conditions incredibly difficult to reproduce and debug. The elusive nature of these bugs can drive even the most experienced programmers to frustration. The problem becomes even more complex in distributed systems. When multiple computers are involved, the timing issues can multiply, making it even harder to pinpoint the source of the problem. Imagine our race happening across multiple racetracks or different computers. The complexity increases exponentially, making it a real challenge to manage. The network becomes part of the race, introducing even more unpredictable delays and making race conditions a nightmare to handle. The added network latency can turn a manageable problem into a chaotic mess. Section 4. Real-world races. Race conditions aren't just theoretical problems, they can have real-world consequences. Imagine a ticket booking system. Two people try to buy the last ticket simultaneously. Both get confirmation, but someone's going to be disappointed at the theater. Or consider a banking app. A race condition could lead to an incorrect balance, causing you to overdraw or miss a crucial payment. These situations can be frustrating and costly. Section 5. Winning the race. So how do we avoid these race conditions and win the race against unpredictable behavior? The key is to ensure that when one thread is accessing shared data, others are blocked. Imagine setting up a system where only one runner can be on a section of the track at a time. Programmers use various techniques like mutexes, semaphores, and monitors to achieve this. These act like traffic signals, ensuring that threads access shared resources in a safe and orderly manner, preventing nasty surprises caused by race conditions.